Okay, scientific measurements. When a scientist reports a measurement, we do it in a very particular way. We want to express how accurately, how precisely we have measured that measurement, right? So we always report all the certain digits and one uncertain or estimated digit. So just as an example, we could look at these two different tables of listing the carbon monoxide concentration in parts per million at the Long Beach site in these various years from 1993 to 2013. So on this table, the concentrations are given with one decimal place, so 6.9, 6.1, etc. Over here, they've been rounded to the whole numbers. So a scientist looking at these numbers gets more information out of this than you might think. We would assume that there's an uncertainty of plus or minus 1 in the uncertain digit. The uncertain digit is always the last digit. So in 6.9, the 0.9 part is estimated. So that would be plus or minus 0.1. So that means we're pretty sure it's been between 6.8 and 7.0. If that's expressed as just 7, well, that also implies plus or minus 1 in the uncertain digit. Here the uncertain digit is in the ones place. So that would be plus or minus 1. And so that would imply between 6 and 8 parts per million. This is not nearly as precise as that. This is really more of an estimate, right? When you're doing this to plus or minus 1, then the difference between 6 and 7 is really not significant at all, right? Whereas over here, the difference between 6.1 and 6.9, that's actually different. Okay, so we need to express our numbers in this particular way. So let's look at some measurements here. And this is something that students have trouble with in lab, and I think it's pretty important, and so I want you to really pay attention to this. We're going to be making a lot of measurements in lab, and a lot of them are going to be using what are called analog devices. They're not digital. The balances we use are digital. Those are easy. You write down the numbers that it shows you. But on a balance like this, a scale like this, there's this line that moves on the scale behind it, and we have to identify what it's representing. So what we do, the number of digits that we're going to write down depends on the device that we're using to measure the thing, right? And so one way to kind of remember this is we talk about read between the lines. What we're going to do is we're going to estimate one decimal place past the smallest division that's given. So in this balance, we're going to ignore ounces because that's English, and we're in chemistry class, we're going to look at the grams. We're going to look at the scale and ask ourselves, well, what does each of those smallest divisions represent? Each line represents 1 gram. The 0 is labeled, the 10 is labeled, but each individual line is 1 gram. So we're going to estimate the next smaller decimal place, which would be 0.1. Okay? When we look at this, there's pistachio sitting up here, and we see that this mark here is between 1 gram and 2 gram, right? There's no uncertainty there. It is definitely more than 1 gram and less than 2 grams. Okay, so if we just wrote 1 gram, that would imply that the 1 was uncertain, but it isn't. So that's not good enough. We're going to write 1 point something. This is where we're kind of guessing. We're estimating. So you look at that and you think, well, it looks like about 0.3. 1.3 grams. And the author said, well, it's 1.2. That's okay, because there's uncertainty in that place. we're not saying that it's absolutely 0.3 or absolutely 0.2. We're saying this is our estimate. But the 1 is certain. We always include all of the digits that are certain and 1 that's estimated. If we're using a ruler, and we do this too, most rulers have the smallest divisions as 0.1 centimeters. And you find something and it's between those two lines, well, it's 0.3 or whatever it is. Then you estimate the next place. Question?
So if something was 50 centimeters, like it lines up on the line exactly, would it be 50.0 centimeters?
So if we're using a ruler like this, and it looks like it's right on 50, and this is the thing that messes students up the most. We're still saying to ourselves, well, the smallest division is 0.1, and so I need to estimate to the second one. And so if it's right on the line, you'd say it's 50.00.
Sorry, the one of mine.
So,
but if it's right on like a whole unit, we're certain of the 50, correct?
yeah, so let's I'm making this little fake ruler here. And so our thing is right here. It looks like it's right on the 50. We can't say that it is exactly 50 because nothing can be measured exactly. And so it's like, well, it's 50, and we know that it's between the 49.9 and the 50.1. When we look at one like this, it's a little harder than looking at something like this, because here it was between lines. And so we could tell, well, it's between 1 and 2, so it must be 1 point something. When it's exactly on the line, what we need to do is just follow the same pattern as we do over here. And so we say, well, I think it's right on the line. Okay, well, how many places do I need? Well, what's the smallest division here? Well, there's tenths. So those are tenths. That's certain. I need to estimate the next place. Does that help?
Yes.
That was a good question.
Because the measurement is in the tenths place, we estimate what's beyond that.
Yes, because the actual lines are tenths, we read between the lines, we estimate 1 decimal place over. So the best way to get a handle on this is, as you're making measurements in lab, come and ask me, am I doing this right? And I'd be happy to tell you. And if you're not, I'll be happy to help you understand what's wrong with it. Okay? So we're going to be using the glass thermometers over there. They have a smallest division that's 1 degree Celsius. So then what do we estimate? The next decimal place, the tenths. So if the smallest division is 1 degree Celsius, you estimate 0.1. Okay? So let's practice a little bit. So here is a glass thermometer, and it's got this alcohol in it. Now, what do you think the unit is?
Degrees Fahrenheit?
Not degrees Fahrenheit,
Celsius?
degrees Celsius. Because it's science. It is hot. It's probably sticking in some boiling water or something. That is really hot. So this is degrees Celsius. I'm just telling you that because otherwise you kind of have to guess. So we're going to look at this and say, well, that's 90 degrees and that's 100. So each of these lines then is 1 degree, right? So if the lines are at 1 degree, I estimate the next decimal place. I'm going to estimate tenths. So I'm going to look at where this red alcohol is. It's not a great picture because it's kind of behind the 100 here. But it looks like it's maybe between those two lines. So this is 100, that line is 103, this line is 104. So I'm going to write 103 point, and this is where we could have arguments.
So you could write like 1 if you want.
Yeah, so somebody might say, I think it's 103.1, somebody might say, I think it's 103.3. There's room for disagreement there.
What about like 103.0?
103.0, I would not mark that wrong. What I'm looking for in your lab measurements is mostly, are you putting down the right number of places? Are you measuring to the right place? Because I'm not going to follow you around all day and see if you measured everything exactly right. I can catch the big mistakes, but I can't catch the little ones, and they're really not that important. Okay? And then, of course, we should put units on there. So any questions about the thermometer? This is a close-up photograph of a 10 mil graduated cylinder, and there's some water inside the cylinder. So there's a curve here. That curved surface of the water is called a meniscus, and we'll learn later what causes that. It has to do with surface tension and intermolecular forces. In glassware, it's calibrated for you to read the bottom of the meniscus. Okay, so if you read the top of the meniscus, you're going to get a different volume than if you read the bottom. So we always read the bottom of the meniscus. Okay, so that's the dark gray here. And then we have to kind of orient ourselves on this cylinder. This is 4 milliliters, and that's 5 milliliters. So each of the small lines is 1/10 of a milliliter, right? So there are lines at the tenths. That means we need to estimate the hundredths. So this is 4. That would be 4.5, and it's less than 4.6. So it's 4.5 something. 4.58 milliliters. Somebody might, I think it's 4.57. That's fine. Okay. Any questions? So that's recording measurements. The precision of the measurement depends on the instrument used. Yeah, question?
So when you're doing things in like medicine or something where you have to be like super precise because people's lives like matter, how do they go beyond like with significant digits you're gonna have tiny bits of error? So
See, the thing is, I'm an analytical chemist. That was my training in graduate school, and I like things that are really precise, and I want to know exactly what stuff is. And I remember giving my oldest son, when he was a baby, some medicine, and recognizing that, well, they sell these different things. You can do it in a little cup. There's the dropper, and then you can also use a syringe. Well, this suspension is very thick, and if you use the syringe, it pushes all the medicine out. If you use the spoon or the cup, some of it stays on the inside, and that bothered me because that's the different volume, right? This is my child. Well, then I realized, yeah, well, the dose of that medicine is for a weight range of child, right? So it might be if your kid weighs between 30 and 50 pounds, they get this amount of medicine. Well, if it's a smidge off on the amount of medicine, is that going to be significant? Actually, it isn't. So medicine is precise, and yet it isn't.
what about like anesthetic?
So the thing is, you definitely don't want to make a mistake by getting the decimal point in the wrong place. Like a factor of 10 difference, that's where people die. And anesthesia is monitored, but I think it's monitored more in terms of watching the vitals on the person than the exact amount, because living things respond to things differently, which is one of the reasons I'm not a fan of biology, because you do experiments there and there's so many variables you can't control for. Doing studies on humans, really, really hard, because their diet, their moods, all kinds of things, their genetics can affect how stuff behaves.
You could take the exact same amount one day and have a different effect.
Yeah, you can take exactly the same thing every day, and depending on your level of activity or how much sleep you've gotten, you could react differently. So very, very complicated. Okay, so we make measurements and we record the measurement based on the precision of the instrument. when we do calculations, we can't have the calculation causing us to think that we have more precision than what we got from the measurement. Because you may have noticed when we do multiplication and division, you may start with just a couple of digits and you end up with like 9. And so, do we need all of those? No, we don't. We need a way to keep track of the precision or the uncertainty in a result. And the more rigorous method is to use differential calculus. You want to do that? Anybody? A couple people might think that's fun. Well, I learned that in college and then I promptly forgot it because I don't need it anymore. So I could figure it out, but I don't want to. We're going to do sig figs. So this is a more simple, practical method of keeping track of uncertainties and measurements. So what we call significant figures, or sometimes significant digits, these are the non-place-holding digits in a recorded measurement. They include all of those certain digits and the first uncertain one. Okay? More sig figs means your measurement is more precise. So how do we count sig figs? How do we determine which ones are not place-holding? So here's a set of rules. All non-zero digits are significant. So in these examples, the bolded ones are examples of what's said over here. So, the 1, the 3, and the 1, those are not 0. So anytime you have a digit that is not 0, that is a sig fig. It's the zeros that cause problems. There's 3 kinds of zeros. So interior zeros, sometimes called trapped zeros. These are zeros that are between 2 non-zero numbers. So that 0 is between a 4 and a 3. That's not just to hold a decimal place. That's a significant figure. Here's a couple more interior zeros. Those are always significant. Then there's leading zeros. These are the ones that come at the beginning of a number. 0.00023. The purpose of those zeros is to hold the decimal place. Because if we left them out, we would end up with 0.23, which is not at all the same. This one also has leading zeros. Leading zeros never count as significant figures. They are important, but they are not sig figs. They just serve to locate the decimal point. And then the trailing zeros. I explain it a little differently than the book does, but you get the same result. So if you like the book method, that's fine. So trailing zeros, the zeros at the end. So here are some zeros at the end. In these examples, there's actually a written decimal point. If there's a written decimal point, you count all the trailing zeros as significant. In these numbers, there are trailing zeros, but there is not a written decimal point. So those zeros are ambiguous. We're not sure what the writer meant. 300. Well, was that measured to the nearest 1? Was it measured to the nearest 10? Or to the nearest 100? We can't tell for sure. It's ambiguous. So you get an ambiguous number like this, and to be on the safe side, we're going to assume the worst. And we're going to say they're not significant. But we're going to try to avoid them. And then we have exact numbers. So if I hold up fingers, how many fingers am I holding up? 3. Is there any uncertainty in that? No. 1, 2, 3, exactly 3 fingers. That's an exact number. We can say that that has an infinite number of significant figures, because we could say 3.00000, and you could say 0 all day long, and it would still be true, right? So exact counting of discrete objects. Those are exact numbers. Integral numbers that are part of an equation. So the diameter of a circle is twice the radius, 2 times the radius. That's an integer that's part of the equation. That number is exact. And defined quantities. So defined quantities include relationships between units. So 1 foot is how many inches? 12 inches. Is there any uncertainty in that? No, a foot is exactly 12 inches because we said it was. Okay? Some conversion factors are defined quantities like this, others are not. If you are within the English system, the relationships will be defined. If you stay within the metric system, they'll be defined. If you go between the English and the metric system, most of them are not defined. Okay, so they're not exact. So we're going to practice counting the number of significant figures. So 554 kilometers. How many sig figs? 3. So there's 3 digits there. There aren't any zeros. Sometimes we look at a whole number like that and think, oh, well, is that an exact number then? Can you count kilometers? Are those objects? No, they're units of measure, so you can't count them. Here's a number in scientific notation, 1.01 times 10 to the 5th meters. 3 sig figs. The nice thing about scientific notation is all the placeholding business comes in the times 10 to the something. And so everything in front of that multiplication sign is a significant figure. In this example, we have a trapped 0, so that would be considered significant anyway. If you had something like 1.0 times 10 to the 5th, even using the regular rules, that 0 would be counted because there's a written decimal point. You'll never have a 0 there without a decimal point. Okay, 1.4500 kilometers. 5. These zeros at the end are not needed to hold decimal places. They reflect measurement. Trailing zeros, written decimal point. We're going to count them. How many significant figures does this number have? 7 pennies. An infinite number of sig figs because it's an exact number. Okay? You can count out 7 pennies without any uncertainty. 0.00099 seconds. 2. Those leading zeros just hold the decimal point. If we put that number into scientific notation, those sorts of zeros would disappear. 9.9 times 10 to the minus 4. Oops. So just a quick review of scientific notation. You put the decimal point after the first non-zero digit. So the first non-zero digit is that first 9. So the decimal point goes there. And then times 10 to the something. The something is how many places did you move the decimal? 1, 2, 3, 4. I moved it 4 places. The tricky part is should it be positive or negative? It needs to be negative. This is a small number. I have negative feelings about small paychecks. How do I feel about large paychecks? Positive. If the number's large, the exponent is positive. If it's small, it's negative. So that one has 2 sig figs. 21,000 meters. 2. The zeros are ambiguous. So we need to assume the worst and we'll say 2. Now, what if that was actually measured to the nearest 10 meters? Well, we kind of have a shorthand way we could underline that 0, and that indicates to a lot of people that's the last significant figure, but it's not very clear. Any question?
Yeah, can you explain the difference between D and F?
So they're both, so you have 7 pennies. What is that infinite number of significant figures, but with?
But 21,000 meters is not.
Yeah.
That's a good question. So why is this one an exact number, infinite sig figs, and this one is not? Because pennies are things that can be counted. Meters are things that have to be measured.
Okay.
Yeah. So let's just say that I know that this was measured to the nearest 10 meters. To indicate that there's 4 sig figs in that number, I need to use scientific notation. So there's an implied decimal here, And so I'm going to move it 1, 2, 3, 4 places. 2.1. Now I can include just the zeros that are actually sig figs times 10 to the, and I moved it 4 places, so I write a 4 there. 21,000 is a big number. I have positive feelings about big paychecks, so it's a positive exponent. So this 2.100 times 10 to the 4th meters, that one has 4 sig figs. Any other questions? Yeah.
Is there anything that has unlimited sig figs that's kind of like a trick, like that makes you think that, like, is there anything on the borderline almost that you'd have to like worry about?
Okay, so we tell you that counting discrete objects are exact numbers. Well, what if you're taking a census of people in a town? It's going to take a finite amount of time to count those people, and people could be born and people could die while you're counting, right? Or you could miscount. So that's sort of a gray area when you get to really large numbers of things. Then you say, well, maybe that's not actually exact. But I'm not going to try to trick you with stuff like that. But something that does happen to students is they see a whole number, like 554 or 21,000, and they automatically say, oh, that must be exact. No. You have to look at how, 21,000 what? 554 what? Well, if it was 554 cars, you can count 554 cars, but you can't count kilometers. Okay? Good questions. Okay, so we do calculations with these measured quantities, and sometimes we gain digits and sometimes we lose digits. And so we don't want the calculation to cause us to gain or lose precision in the answer. So we have to have some rules again. So multiplication and division are related operations, and so there's one rule for both of them. In multiplication or division, the result carries the same number of significant figures as the factor with the fewest significant figures. So 2 examples here. 1.052 times 12.504 times 0.53 equals, and this is what your calculator says. We need to round this to reflect the actual precision. So we look at each of these numbers that are being multiplied and we ask ourselves, how many sig figs? Well, this one has 4, and this one has 5, and this one has 2, because that leading 0 doesn't count. And then the hard part, which is smaller, 4, 5, or 2? Well, 2 is smaller. That means I round this number to 2 digits, 2 sig figs. So I could underline the 7, and that's what I'm going to round the number. In this example, we're dividing. We have a number with 5 sig figs, and we're dividing by a number with 3 sig figs. 3 is the smaller number of sig figs, and so we round the answer to 3 sig figs. Again, that leading 0 doesn't count. The other broad category of operation is adding and subtracting. You have to have a different rule. It's very similar, which is good and bad. So for adding and subtracting, again, we're looking for the fewest number of something, but here it's the fewest decimal places. So you look at the numbers that are being added and subtracted, find out which one has the fewest number of decimal places, and that's where you round your answer. So in this example, the first number has 3 decimal places, the second one has 2 decimal places, the third one has 4 decimal places. The middle one, 0.07, has the fewest number of decimal places, 2 decimal places. So I'm going to take the answer that my calculator gives me and I'm going to round it to 2 decimal places. So let's look at why that rule is. Well, in this number, we're assuming these are measurements, 2.345, which is the uncertain digit? It's always the last one. So the uncertain digit there is the 5. I'm going to underline the uncertain digit. That's the last sig fig. In 0.07, what's the uncertain digit? The 7. And in 2.9975? The 5 is the last one. So when I do the math, I'm adding 5 to a blank space and a blank space. Do I have any clue what those digits are? No. So I have to assume it's 0, but I don't know. And I'm not certain about the 5. So when I add 5 to nothing and get 5, is that a certain digit? No, that's uncertain. So I'm going to underline that one. Here I'm going to add a 5 that I'm uncertain about and a blank space. I'm certain about the 7, but because I'm adding this other stuff to it, the result is also uncertain. So the 2 is not certain. Over here I've got a 4 and a 9, positive about those. I'm really confident in those. But the 7 is uncertain. So when I add those up and get a 1 here, that's not certain. There's uncertain. Okay? Now I've got a 3. This is definitely 0. And 9. And so all of the rest of this math, all of those digits are certain. So just as with a measurement where we include all of the certain digits in the first uncertain one, just one, in this result we want to include all of the certain digits in the first uncertain digit. And so the first uncertain digit is this.
Why is that one uncertain? Is it because you always guess the next decimal place?
Well, the 1 is uncertain because the 7 was uncertain.
Because the 7, since
It's the last decimal place. It's the last digit in this measurement.
Yeah.
The last digit is always uncertain. And because that's part of getting to this 1 down here, the 1 is uncertain also. So that's a good understanding way to do it. A practical way to do it, we've stacked all these up pretending that we were going to do long addition without a calculator. Go ahead and use your calculator so you get the right answer. Write it down, make sure that all your columns are lining up. And then one thing you can do is you can just go from left to right and find out which of these numbers stops first. Well, this one ended first, so I'm going to draw this line just to the right of the number that stopped first. And that is the line where my answer is going to stop. This is a subtraction example, 5.9 minus 0.221. And we see that 5.9 stops here after the first decimal place. So I draw a line, and that tells me that my answer is going to stop after the first decimal place. Calculator says 5.679. I'm going to keep this place. We'll talk about this in the next slide. And we're going to round this up, because we're going to round it up to 7, because 5.679 is closer to 5.7 than it is to 5.6. Any question?
We keep the first uncertain, right?
We keep one uncertain digit. There's no point in keeping the rest of them because they're like crazy uncertain. But we want to keep one because there's information there, and we don't want to throw away information. Rules for rounding. So you figure out how many sig figs you need, and then we have to round. So we look at the next digit, the first one that's going to get dropped. If it's 4 or less, we round down. If it's 5 or larger, we round up. It's really important when you're rounding numbers that you do not change the magnitude, the overall size of the number, okay? So if you're rounding in the tens place, the hundreds place, the thousands place, people end up with some really crazy stuff sometimes. So let's make up an example. Let's say that this is the price on a house for sale. $256,493.75, okay? And we say, well, that's a little ridiculous to go out to the cents, right? Let's round this to the nearest 100. So if we're rounding it to the nearest 100, we're rounding it here. That would be 4 sig figs, right? And you look at the next digit, it's a 9, so that tells me I round this up to a 5. And I sometimes get students giving me this answer. They've rounded the value of that house to $2,565. Hey, I'll go for that. I could flip that. Super easy, right? You don't change the magnitude of a number when you round it, okay? So how do we avoid that? Well, we're going to have to stick some zeros in here. So if you're rounding in the tens place or the hundreds or whatever, you stop that here, and then you have to replace those digits until you get to that decimal point. You have to replace those with zeros. So you could do that. And that's reasonable, rounding $256,493.75 to $256,500, right?
But you don't put.
I don't want to put .00 after it. Right, because if I'm trying to get 4 sig figs and I write .00, that decimal point made all of those zeros significant, and now I've got the same number of sig figs I had before. So we don't want to actually write the decimal point, but we need the placeholder zeros. A better thing to do is to put this number in scientific notation. So I'm going to move the decimal point over there, 2.56, and then I can go ahead and round that 5, and I can just drop the rest of it, times 10 to the, and then I figured out, well, 1, 2, 3, 4, 5. 5 places, and big number, positive exponent. So 2.565 times 10 to the 5th dollars. Okay, so watch out for this. I'm just going to do this, this one here. So if we're rounding 5.349 to 2 significant figures, I like to underline that last digit that I'm going to keep, that's the uncertain digit, and then just look at the next digit. Don't start at the far end and round your way back. It's a lot more work and sometimes gets you the wrong answer. I'm just going to look at that 4. The 4 tells me I'm going to round down, and so this is 5.3. If you start at the end and take the 9 would make the 4 round up to a 5, and then 5 would say round the 3 up to a 4. So don't do that.
I got a question.
Yeah.
How would you, never mind.
Is this?
Right here, that's just.
Okay. So sometimes we do a calculation, and then we end up taking that number and doing another calculation on it. We want to avoid rounding errors. If you round every single step, you're going to introduce error into your measurement. So we want to avoid that, so we only round at the very, very end. We carry extra digits along. So my rule is to carry a minimum of 2 extra digits. If you want to keep all of them, that's fine. It just gets a little tedious punching in and writing down all of those numbers. And so I've kind of thought about it, and it's like the minimum you need is the correct number of sig figs, and then just write down 2 more digits. You don't even have to worry about rounding them or anything, just write them down. Okay, so I will be following that pattern. So let's look at what's happening with this example. 6.78 times 5.903 times the quantity 5.489 minus 5.01. So we have subtracting here and we have multiplying. Those use different rules for keeping track of sig figs. So I'm going to look at the subtraction. I'm going to do the subtraction and write down what my calculator shows me, 0.479. If that was a final answer, I've got 3 decimal places and 2 decimal places. This should end in the 2nd decimal place. If that was all I was doing, I would round it to 0.48. But that's going to be used in the rest of the calculation. So what I do is I underline the last significant figure, that uncertain digit. I keep the extras, at least, well, this one, it was all of them, but at least all of them or 2, whichever's smaller. Whichever's, yeah. So then I do the multiplication. For multiplication, the rule is how many sig figs, not how many decimal places. So this one has 3 sig figs. This one has 4 sig figs. This one, it's showing 3 digits, but it's only 2 significant figures. And I know that because I underlined this one to tell myself, no, this one only has 2 sig figs. So then here's the answer my calculator gives me, and I'm going to round that to 2 sig figs. So that's the first 2 digits, the 1 and the 9. And I look at the 1, which is the first one I'm going to drop, and I round down, and the answer is 19.
So you lose a lot of accuracy.
Well, it looks like I'm losing a lot of digits and stuff. But the thing is that this difference here didn't have a lot of precision. This difference was pretty small, and so because this only had 2 significant figures, that's why this number ends up with only 2 significant figures. Sig figs are not a perfect way of doing this, but they're quick and easy once you understand how they work. Okay, let's do some examples. So get your calculator out. So we got 3.10007 times 9.441 times 0.0301 divided by 2.313 equals. So I've got the value of my calculator here. I don't like writing down 9 digits. So what I'm going to do is I'm going to think about how many do I need. So I ask myself, well, how many sig figs here? Well, that's, 6, right? And this one has 4. And this one has how many? 3. Leading zeros don't count. And this one has 4. So the smallest number of sig figs is this one, 3 sig figs. That tells me my answer is going to get rounded to 3 sig figs. So I think about that as I write my answer down. So 0.380, there's 3 sig figs. And I'm going to write down the next 2 digits just as extras, sort of insurance. Then I'm going to round it. 0.381 is the correct answer. Couple of reasons for writing this down. What if I want to go back and check my work, or I realize, oh shoot, that should have had 4 sig figs, and all I wrote down was 0.381. Then I have to go do the calculation all over again. If I wrote down some extras and I realize I didn't include enough, I can just go back and round it again. That saves time. Or I might find out later that I need to use this number in a calculation. I don't want to use the rounded value. I want to use some extras to avoid rounding errors. Any questions about that one? Okay, the next one, adding and subtracting. Do not overcomplicate this. Just do it in your calculator. 0.881 plus 132.1 minus 12.02 equals. Usually with adding and subtracting, we don't get ridiculous numbers. So you might just write them all down. 120.961, there's not too many of them. Rule for adding and subtracting is the fewest number of decimal places. So this one has 3 decimal places, this one has 1, and that one has 2. So we'll go with 1 decimal place. We'll keep the 9. The next digit's a 6. That makes the 9 round up to 10, right? So we get 121. We need 1 decimal place. So 0.0. Sometimes you have to put zeros back in. Your calculator won't show you zeros like that. Questions? We'll get practice on the worksheet today. Okay, Okay, this one's mixed. We've got multiplying, dividing, and adding. The parentheses tell us we should do this first. So 44.11 plus 1.223 equals. I'm going to write that down.
Can I ask you about me?
Yeah.
So that's by doing that, you're saying you have 4 sig figs instead of just putting 121 and it only being 3 sig figs.
Right. Yeah. So 121.0 is 4 significant figures. And because of where this came from with adding and subtracting, the number of decimal places is important. You can't predict how many sig figs are in this answer based on how many sig figs are in the other numbers. With adding and subtracting, you can gain or lose significant figures. So this is what my calculator gives me for the result of this addition. I need to use the adding rule for sig figs and say, well, this one has 2 decimal places, this is 3 decimal places. That result should have 2 decimal places. So I'm going to underline the last significant figure. Now when I do multiplying and dividing, I'm looking at number of sig figs instead of number of decimal places. So I'm going to go ahead and do the math. 2.5110 times 21.20 divided by the 45.333. And this is giving me a whole mess of digits, right? How many sig figs in this one? 4. 5. Yeah, that 0 counts. And this one? 4. And this one? 4. So 4 is the smallest. My answer should have 4 significant figures. So I'm going to think about that as I write this down. There's 1, 2, 3, 4. There's my 4 sig figs. Write down the next 2 digits. 7, 0. You don't have to worry about rounding or anything. Just write them down. You got a different number. Oh, I screwed up. I had 2.544 instead of 2.511. Thank you. Let's try that again. It's one of the things I like about this calculator is you can see what you did and you can go back and just, yeah. Okay, so 1.174, there's my 4 sig figs. 27. Don't feel bad about correcting me. I make mistakes all the time, and I'd rather fix it right here in lecture than have somebody come back on YouTube and make some comment about how stupid I was. I do stupid things. Okay, so then we write down the 2 extra digits, then we round it, and so 1.174. Okay? Last one, this one's similar, but now because of the parentheses, we need to do the multiplying first. 12.01 times 0.3. So that gives us 3.603. How many sig figs in that result? 1, because we multiply by 0.3. So that has 1 sig fig. I take that and I add the 4.811. And the calculator gives me 8.414. So I've got adding, I look at decimal places. This one ends in the ones place. It has 0 significant decimal places. This one had 3. So this one ends in the ones place. The answer is 8. If we stack those, 3.603, 4.811, understanding that that's our last significant figure, then we draw the line here. And it's just 8. Some people find that disturbing. sometimes the thing that you're adding is so small relative to the uncertainty in the number that it doesn't even make a difference. So if you think of, say, a semi-truck with a load of peaches, and it goes to the scale, the truck scale, and they weigh it, and then somebody comes running up, oh, hey, you dropped this peach, and they toss it up onto the truck. Do they really need to re-weigh the truck because they put one peach on there? It's not going to make any difference, right? The truck weighs tons, and that peach weighs less than a pound. Adding that on is insignificant to the whole thing. Questions? Yeah.
Would you put the decimal after the 8 when we're answering?
That's a good question. Would you put the decimal point? You could. It's not going to make a difference in this case, but it kind of looks silly, right? So I wouldn't. If there's a 0 at the end, then the presence of the decimal point makes a big difference. So I've been throwing around this word precision. Let's talk about what it really means. So precision and accuracy are different things. Accuracy is the first one there. Accuracy refers to how close the measured value is to the actual value. Is it correct? Precision refers to a series of measurements. You can't really have precision with just one measurement. A bunch of measurements, how close are they to each other? And you can have accuracy without precision. You can have precision without accuracy. You can have both of them, or you can have neither. So let's look at an example. 3 students, they're each weighing a lead block that has a true mass of 10.00 grams. And they're coming up with some numbers that are a little bit different. So they each did this 4 times and did an average. And there's a table with their results. And you look at that and you're like, wow, that's lots of numbers. Kind of hard to look at. We can make graphs and it becomes more of a picture and it's easier to see what's going on. So here, student A. The blue line here is the true mass of the block. The red dotted line is the average of the student's results. And then each of these purple bars represents the individual results. And so we can see there was a lot of variation between those 4 results. They weren't even close to each other. So we say that this is imprecise. And then we look at how far is the red line from the blue line. Well, it's kind of far away, especially since we know this is 10.00 grams. It should be within 0.01 grams of the true value. So this is not accurate either. So this student really blew it. Here's student B. Student B, all these purple bars are really close to each other. That's good precision, very consistent. Unfortunately, this student is consistently wrong. So the average that person comes up with is 9.79 grams, which is significantly smaller than 10. Because 9.79, in that average, the uncertainty is in this 9, right? And yet this is differing significantly from what it should be. Student C nailed it. Here we've got the purple bars being almost all the same height, very close to each other. And when we do this average, we find the average is 10.01. The true value is 10.00. The difference there is in that uncertain digit, so this is really good. That student's results are accurate and precise. We would always love to have accuracy and precision. It's not always possible.
So is that what the standard deviation and all that's for?
Yeah, we'll get to that, I think, in experiment 1A. We'll be making some measurements and looking at standard deviation and percent error. And the percent error tells us how far away from the true value our result is. And standard deviation is a measure of how different the values are from each other. It's kind of a preview. So student A, inaccurate and imprecise. Where does that imprecision come from? Why is it all over the place? Well, often that's from random errors. There's two kinds of error. There's random error and systematic error. Random error is random. It might make our result too high. It might make our result too low. When you average a bunch of measurements, the random error generally goes away because the high and the low ones cancel each other out. Systematic error is more troublesome. This is an error that's usually either high or low. So student B, the average was low and all of the values were low. There was a systematic error going on. Could be caused by not using the instrument correctly. It could be caused by the instrument not being calibrated or some other factor that we're not aware of. And student C has very little systematic error, very little random error, and so that's what we would always like to have. But you'll see in lab that we often measure things or do something 3 or 4 times. And that's so that we can average it and calculate a standard deviation and get an idea of how precise our numbers are. Sometimes we don't know what the true value is. But if we have a precise value, that suggests that it might be accurate. Not always, but it's a good sign.
You said